Very good morning, good day to everyone. This is the another webinar in the series of advanced air mobility, and this topic is this presentation is given by Dr. Satya Chakravarthy. Satya Chakravarthy is a professor of IIT, at IIT Madras. He graduated from Georgia Tech in the US and went back to IIT Madras for starting his career, I believe. And the significant thing that he did is he started a company called ePlane, I believe in 2019, and he is going to talk about his experiences of advanced air mobility and how he is contributing with his team. So then and you can ask any questions on the chat, and we will answer them at the end. So yeah, please go ahead, Dr. Chakravarthy.
Thank you so much. I think we need to acknowledge IEEE Vehicular Technology Society for the sponsorship of this webinar series on advanced air mobility. The topic that I'm actually going to be talking about is eVTOLs as harbingers of electric aviation. I'm quite passionate about electric aviation myself. And when I thought about electric aviation, there was a reason why we needed to actually go to eVTOLs, but I also feel that we will actually do eVTOLs as a precursor to electric aviation. So that's the theme of this particular talk. And as you will see how this emerges, you will see how the pattern happens. So the contents of this talk is, first of all, I will introduce advanced air mobility just as a cursory introduction, just for the sake of completeness, and why not electric planes and the role of electric planes in advanced mobility. Would electric planes be commercially feasible? How would electric planes need to be different for them to be more accessible? We will have a little bit of a double clicking on the Indian market where we work out of, and it's actually one of the largest such markets, particularly on aviation. So it's useful for everybody in the world to be clued in on what's the Indian aviation scene is looking like. And then we will actually focus on the tech and the shift to eVTOLs in the ecosystem. We also actually have to worry a lot about these infrastructure. So we will talk about these vertiports and so on. And how do you actually get these to function in cohesion with existing aircraft, the air traffic control, pilot training, ePlanes pathway towards implementation, and so on. So this is how we are going to be structured. So the whole idea of advanced air mobility is predicated on about 5 pillars. One of them is actually sustainability. That's a big thing that's happening around the world, and we are no exception. But what we really care about is accessibility and efficiency. How can aerial modes of transport be accessible to large segments of the human population? And correspondingly, how can it actually make economic and societal impact? But on the left-hand side is actually the technological side of things. Because of the advent of certain technological advancements and the possibility of automation and hence safety, it's possible for us to actually imagine a world with advanced air mobility as we would be talking about. So I actually come from a combustion background, going to Georgia Tech and coming back to India and working for the last, I think the previous 30 years on combustion. And I was actually establishing the combustion center at IIT Madras when we found electrification of cars and thermal power being replaced by solar. These are the couple of pillars of the combustion center that I was working on. And the third one, of course, was aerospace propulsion, which was kind of like a safe haven for me to continue to work in the area of combustion on those applications. But I asked the question, how long will it actually take before aircraft also actually start getting electrified? And so that's why we wanted to basically say, what does it take to electrify planes, and what are the issues associated with it? So the idea of actually electric planes in advanced mobility is actually quite far-reaching. First of all, about the adoption and growth of electric planes. There is increasing popularity and market penetration that is possible with electric planes. We will see why that is the case. from a cost structure point of view. For example, government incentives and subsidies that are available for electric planes, infrastructure development. There is a whole new set of infrastructure that actually has to come about, but not very intensive, capital intensive though. And how do you actually get consumer shifts and awareness to happen? On the environmental benefits, obviously, there is reduction in greenhouse gases, improved air quality, energy efficiency, and sustainability in vehicle production as well. It's not just the product that we we are actually sustainable on, but also even the production of the vehicles, we want to actually be sustainable. And the tailwinds in this particular sector is actually about the urban air mobility sector growth globally that is predicted in the next 15 years. What are the different UAM market segments, and what's the kind of energy efficiency that we can actually bring to these markets in terms of charging infrastructure, the batteries, and all of those aspects from a market standpoint. So the question that we have to ask, if you are just thinking about electric planes as something that's at least replacing some of the current aviation planes which are going from airport to airport, is it actually commercially feasible? That's a question that we have to ask. We have to then ask the question, what is the kind of cost that we are actually having with the current planes, and look at developing these electric planes from a business standpoint. Does it make sense from a business standpoint? Currently, if you actually look at it, there is a fairly high asset cost to these planes, which requires us to have complex leasing arrangements between the OEMs and the airlines, and so on, so that each of those different businesses can manage their own cash flows within reasonable times of time periods. But more importantly, I think the problem is actually with the high operation costs. And one of the reasons why you actually have a high asset cost is engines are actually about half the cost of the plane itself in the first place. And so if you were to actually get the engines out of the picture, the fuel out of the picture, and all of that stuff, the asset cost can come down. And for the same reason, maintenance of aircraft is actually more and more about the engine rather than about the aircraft. So the engines actually demand lots of maintenance when compared to the aircraft itself. So if you actually had engines, you have a huge maintenance cost. Plus, you also have the operation cost, including fuel cost. And in the case of fuel, the issue with that is quarter on quarter, the international crude prices keep fluctuating. And it's actually difficult for airlines to predict what will their margins be in the next quarter, with which they can actually plan accordingly. And this is actually keeping them always on their toes. And you will find that very few airlines in the world actually make profits. And partly because there is a high and fluctuating fuel cost that they have to deal with. And all of that finally translates to the customer. You're actually looking at this being expensive for the people, and of course, low profit for the businesses. And while we are here, we want to also indicate that it's not just about the people transport, but also cargo transport, like, for example, aerial cargo transport with cargo aircraft is also something that we want to keep in mind. So how can we actually make electric planes to be different so that they can be more accessible is the question and the motivation for me to be working in this area. What we found was that the asset cost actually can be lowered, and I need to explain this a little bit. If you were to actually take an existing plane as an example and then replace its engines and the fuel tank and with, let's say, batteries and motors, and assume that the motors are actually much lightweighted, so it's primarily the batteries that are going to occupy much of the replaced weight, but the total weight of the aircraft is about the same. You have two consequences of it. One is actually you will have an extremely limited range by virtue of using batteries when compared to fuel, but we will target that problem next. But talking in this context, because you have a limitation on the amount of battery you can put, and battery being like a significant chunk of the cost of the aircraft, there is a good opportunity for you to lower the asset cost when compared to a engine-powered equivalent aircraft. Of course, if you're taking things like small aircraft with piston engines and single propellers, this cost comparison may not really work out very well. But as you progressively go to larger and larger planes, an electric aircraft can easily be shown to be cheaper when compared to its corresponding engine counterpart, although with a much shorter range, as I pointed out. But that said, I think from an Indian context, actually a lower asset cost comes from manufacturing and designing and developing and certifying in India. That's another thing that we could actually bring to the table from my perspective. And the second thing, of course, is electric vehicles in general and planes as well require much less maintenance when compared to their corresponding engine counterparts. So there is a very little amount of maintenance costs that you will have. And similarly, similarly, we will also actually find that electricity costs are low as well as flat. And therefore, you can, first of all, actually reap benefits from the low cost. Plus, more importantly, you can actually predict what your cost is going to be in the next quarter. So it's one of those boons for an airline business to be in. The next problem is actually the thing that we talked about is short range. So if it's possible for us to then utilize underutilized takeoff and landing infrastructure. So what we find even in India as well as in other parts of the world is there are lots of Second World War vintage airstrips that are kind of lying unused. And these are fairly close to each other. It's just that we have not been developing them into full-fledged airports and so on. So when you now have these short range, is it possible for you to start utilizing these and then get people to go short distances even with electric aircraft? And that's something that has not been happening because existing aircraft are meant for longer ranges. And in fact, they are meant for such longer ranges that hardly gets utilized in reality. A typical Boeing 737 would actually have like about an 8,000 kilometer range, but usually it does lots of these hops that are anywhere between 400 to about, let's say, 2,000 kilometers kind of distances. So it hardly actually utilizes, or even if you actually dial back to like a Cessna, a four-seater Cessna, which has actually about a 1,600 kilometer range, you hardly see like a Cessna flying a 1,600 kilometers in a single fuel tank capacity. So combustion planes are actually kind of like overrated. We don't really need those planes as such. A more appropriate technology would be electric planes, particularly if you are able to start utilizing these underutilized takeoff and landing infrastructure. All said, if you're not going the route of doing autonomous aircraft without pilots, it's possible for us to actually bring down the cost of aviation to 50% of what it is by simply looking at the asset cost and the maintenance and operating costs. Of course, if you actually in the future, if you were to actually get down all the way to autonomous flights, we can actually bring down the cost of aviation to 90%, down to 90% of what it is today. And that means that lots of more people can actually afford to fly and more frequently to even much shorter distances and so on. So this is the overall picture that electric aviation actually paints for us going into the future. Just a double click on the Indian market, wanted to actually differentiate this when compared to how aviation is usually viewed in the context of the larger global situation. So one problem that we have to actually tackle is scalability, which means that we need to be able to get more and more passengers to get into these planes and get actually more charging stations to be there and all of that stuff. That's a scaling that we have to look at. When you now talk about more passengers, the starting point is more human beings, and that's actually where India plays a very good role. Now, if you look at typical aircraft in terms of number of passengers and the range of the aircraft, larger the number of passengers of the aircraft, like larger the aircraft capacity, typically it also has a larger range, and it actually makes economic sense to build a larger plane that goes farther for that set of people to be taken together. However, in the Indian context, even for short distances, you will actually find enough number of people. And that essentially means that an electric plane can actually be as large as it can get, and like a conventional plane. But let's say it actually has a limitation on how far it can go, you will still be able to find people over there. And that's essentially where you should be able to tap into these unutilized landing takeoff infrastructure, where we can actually start getting economic activity done much faster in tier 1, tier 2 cities, in rising urban centers that are actually not so urban so far. And that's where the economic impact is something so huge. However, let's actually look at the present day scenario and see where it's actually taking us today. First of all, the technology here actually has far fewer moving parts because you're having batteries that are directly connected to motors that turn propellers in turn, and so on. So you don't really have engines and shafts and transmission and gearboxes and all of those things that go with the conventional engines, which essentially means that you can miniaturize these motors, have multiple propellers in front of wings or appropriately located places to take advantage of what's called as distributed electric propulsion, and get much better aero propulsion integrated architecture that enhances the lift or reduces the drag, and get some currently out of the world aerodynamics to the table. That means your lift to drag ratio for these aircraft can be significantly higher simply because of adopting electric planes. On top of it, if you actually were to shift to fully carbon fiber composite bodies, that gives you lightweight aircraft. It also means that we can extend the range simply by lightweighting the aircraft, in addition to the aerodynamics. In fact, if you look at like a range equation for an electric aircraft, you don't have the advantage of the aircraft getting lighter because of the fuel getting consumed and making the aircraft lighter and emitting exhaust gases behind. The battery remains there all the time. So in some sense, the consumed part of the battery during a flight is actually a dead weight that the aircraft carries, which is sort of inefficient. So all said, you can still show that the range is directly proportional to the battery energy density, the lift to drag ratio of the aircraft, and the payload to the total weight of the aircraft. Which means that if I were to lightweight the structure, I can increase the payload fraction on the one hand, and the lift to drag ratio could actually be increased at least to be about double or triple with distributed electric propulsion and so on. So there are other ways to increase the range in the modern technological landscape of aviation than just focus on the energy density of the battery alone, which seems to be something that will keep on improving in the next few years as we go along from where it is today to maybe towards the end of this decade, where we can start looking at about 1,000-kilometer kind of ranges that are a lot more optimal for electric aviation to play out much more economically. So the central part of the tech is to actually replace battery pack, energy IC engines as well as, I mean, many of us do not clearly understand that gas turbines are also actually IC engines, but IC engines otherwise are normally considered to be ones used in cars. But whatever it is, the combustion engines can actually be replaced by battery packs. However, with the current level of technology, the range that we can get is actually too small to even fly between existing airstrips, even if they are unutilized airstrips. And typically, these in some parts of India and other parts of the world, you could get to find airstrips that are within the 30 to 60-kilometer distance, which is actually fairly conducive for today's electric planes to do even multiple trips. But if you are actually looking at any distances that are of the order of about, let's say, 200 kilometers, then it's kind of at the edge of what an electric plane can do today. And that's not good because you want to actually still have some reserve capability by the time you land, just in case you're not able to land and you need to loiter around and come back to land a second time, and so on. So that's not very good if you don't have a more than about a comfortably more than about a 200-kilometer range. This necessitates us to actually go for something called vertical takeoff and landing. And then the question is, what is the kind of space that you need for vertical takeoff and landing so that you don't need to have airports for this purpose and so on. So we have to then focus on how to reduce the requirement on the infrastructure in terms of the actual space that you need to land, because the regulations actually specify the space for landing in terms of a multiple of the maximum dimensions of the aircraft. So we have to actually look at how to make the aircraft to be of the shortest wingspan. And then you have to ask the question, do you really need to have wings if you're going to take off vertically? The answer is yes, that's what actually gives you some amount of range, and therefore you need to have the wings. But is it possible for us to actually have a very compact wing that can actually do the job for you? And that's something that we will actually talk about in the future. But we also actually have to look at a new airspace where you could have obstacles that come in your way. It could be static obstacles like skyscrapers, high-rise buildings, but it could also be dynamic obstacles like flocks of birds or other such eVTOLs that are flying around and so on. So those are things that we have to actually focus on. So if I were to actually then shift from a conventional aircraft that could be electric but does not give the range to a eVTOL, then I find that you can have a new market to tackle, which is an urban air mobility as well as a regional air mobility within the distances. Let's say if you're looking at urban air mobility, it should be in the somewhere between 10 to 30 kilometers kind of distances that will take you from a center of the city to its periphery or outside. And regional air mobility could be between two adjacent towns that are not too far apart, sort of thing. And taking this effort in starting to do with cargo, for example, to begin with, which is unmanned, is actually a very good, sensible thing to do. And then start doing regional air mobility, which is rural, and then get to putting people on board. And then we want to get to the city center, like the urban air mobility piece. And when you're now starting to put people, I think the first kind of use case that we have to worry about is air ambulance, because we still find road ambulances getting stuck in traffic, which we want to avoid for critical care patients. And so we will actually focus on things like air ambulance before we actually get to urban air mobility. And then ultimately we want to get to larger and larger aircraft as we go along to get conventional takeoff and landing for intercity applications. So when you now look at the societal impact of eVTOLs, obviously there is zero operational emissions. It's possible for us to also show that the net cycle of the battery processing all the way to battery recycling, all of that put together, the net emissions, not just from an aviation point of view, but if you're able to imagine that a slice of the road traffic could actually be removed with eVTOLs, we could actually show that there is an impact in terms of the road emissions that actually we see from cargo as well as passenger movement on let's say taxis and other trucks and so on. And definitely the distance, the time it takes to actually cover a distance of about 10 to 20 kilometers or 30 kilometers within a city, for example, can be done within about 10 minutes as the crow flies, as opposed to actually having to wade through traffic intersections and take turns left and right, as well as getting stuck in traffic, which might otherwise take you anywhere between half an hour to about 1.5 hours, let us say. So you have an ability to actually cut down the travel time to about 3 to 8x when compared to road travel. And that essentially means that the asset can actually be repeatedly used for multiple more trips. And all that basically means is you don't need as many eVTOLs in the air as you have the number of road vehicles for doing the same kind of movement of goods or people. And that can actually declutter urban spaces. With fewer aerial vehicles, you can actually remove more vehicles on the road. That's a basic idea, which gives you that 7 to 8x faster travel time. So and that's essentially how we can declutter urban spaces as well. So what are we essentially looking at for the pieces of this puzzle to go together? First of all, I think as you can see around the world, there are OEMs that are actually focusing on developing the aircraft itself, and that's kind of like the major focus that people are actually working on. But it's not just the plane alone that matters. You need to work on lots of other things in tandem. And so for the OEM, actually, of course, we through the ePlane company that Kamlesh introduced me about as an example. But fleet operators and management is something that we have to worry about. Pilot training entities and regulatory authorities are actually somebody which is very, very important. In India, it translates to Ministry of Civil Aviation and Directorate General of Civil Aviation, which is the equivalent of the US FAA or Europe's EASA. We need to actually have commercialization partners, such as people who would develop and manage vertiports, people who would actually provide charging infrastructure and maintain those and all of that stuff. Plus, of course, you need to finally have the consumers who will actually consume for either transporting goods or people. So just one slide on how we are going about doing this. On the aircraft side of things, the OEMs part is to be developing India's first electric flying taxi with specifically for focusing on air ambulance applications to begin with, and then subsequently we'll actually get into the air taxi business itself. Is actually the most compact winged eVTOL in the world, with about an 8-meter wingspan kind of footprint, and with a capability for about a pilot plus 2 passengers. And in the air ambulance case, it would be what should I say? A pilot, a patient, and a paramedic to go with. And of course, these distances we are clocking are in the 10 to 15-minute kind of time frame. A paramedic is sufficient. You don't need a doctor, even if it is critical care, is our current hypothesis. But we can upgrade to a 4-seater, including a doctor if required, as well as, of course, make that 4-seater useful for taxi applications as well over time. The current range that we are actually looking at is about 100 kilometers, 110 thereabouts, but with the outlook that it will actually become about 200 kilometers. Beyond the 200 kilometers, we will actually focus on increasing the payload. If it's possible for us to get to 5 passengers, that is pilot plus 4 seats, and so on. So there is a combination of passengers versus range that is doable. And of course, from getting to 200 kilometers, we could actually push the range further and further with newer battery chemistries. We can actually talk about it maybe in the Q&A if somebody wants to ask questions about it. And perhaps also actually think about fuel cell applications, which could get us past the few hundreds of kilometers kind of range to 1,000+ kilometers range as required, maybe. So a cabin size of about 3 meters to 1.5 meters, a fairly spacious cabin over there, and then a total mass of about close to 2,500 kgs, and a lithium battery charge of about 20 to 30 minutes with 80% recharge. The next couple of slides that I actually will focus on what's the kind of infrastructure that we are looking at to go with the ePlane. There are essentially 3 kinds of landing spaces that we need to be worried about, and these have a few different requirements. First of all, what is the kind of space that's available, and how are we actually sticking to regulations on these spaces, because these are now highly regulated with specific markings and areas that are actually allocated for parking, as well as a carriageway in between, and then what's called the FATO, where you actually will take off from. And all of these dimensions for the taxiway or the parking bays and the FATO all depend on the dimensions of the aircraft, and they are like small multiples of the aircraft dimensions itself. And therefore, the shortest of these aircraft dimensions will get you the most accessible spaces, like the rooftops of buildings. And if you actually have a rooftop of a building like the one that we're seeing over here, this would actually what would constitute like a vertiport, where we have the ability to park about 2 or 3 aircraft at the same time and have 1 or 2 of them actually put on charging, while the other ones are taking off and landing. Again, we actually have an ability to look at multiple different kinds of charging infrastructure. A verti hub could actually be something that has about, let's say, about 10 parking spaces, 8 to 10 parking spaces, where you can do a long duration charging. And this long duration charging may not be very long. It's not like your 6 hours kind of charging. It could be shorter than that, mainly because eVTOLs actually come with a higher discharge capacity, and therefore it's also possible for us to charge them faster without the batteries getting too heated up. And of course, while we are charging, we could modulate the temperature of the batteries on the ground with additional infrastructure to keep the temperature of the battery pack constant, regardless of what your external temperatures are, whether it is too hot or too cold kind of situation. So the verti hub is actually very conducive for what would I call as a slow charging, whereas the verti port, which is actually only about 2 to 3 parking spaces, could probably be having a fast charging prospect. But then we could also actually have something called a verti stop, which is just about a space for 1 aircraft to just land and take off. And in this kind of a situation, you still could think about some amount of charging that's kind of like a flash charging or a ultra fast rapid charging, whatever you want to call that, which could actually charge within like, let's say, about 5 minutes or so, and just top up the SOC by about 10% or 20% within that time when passengers are ingressing and egressing. And if you have to actually, if the pilot has to do so the pilot actually has to double up for security check, maybe, as well as also do like a visual inspection of the aircraft around, that's mandatory perhaps. All of that stuff is regulations that are evolving as we speak on what should actually be the standard operating procedures for a single pilot operation, in which case you get enough time for a rapid charging to happen that can increase the top of the SOC, so that we will be able to actually get, let's say, a 4th trip in a single charge or a 5th trip in a single charge sort of thing. I shouldn't say single charge there, but let's say before we have a downtime for a slow charge. So the whole approach here is to develop a very compact aircraft that doesn't require too much of a urban space to land and take off from, which can also do multiple short urban trips in a single charge before it needs to actually have a downtime for a slow charging, so that you will be able to optimize your battery life on the whole, and bring down the cost of travel to something that's just about like about a 1.5 to 2 times the Uber fare. So for a regular customer. So that's the kind of price points and the cost structure that we are looking at, where these vertiports, the charging, all of that stuff will play a big role. So that said, what is actually about the airspace, right? So in India, as well as in other countries, drones are actually allowed up to about a 400 feet above ground level. And on the other hand, we actually have conventional aircraft, which are conventional takeoff and landing aircraft that have an air corridor above the 5,000 feet above ground level. So there is an in-between space that today probably helicopters use, but very, very infrequently. And this is the kind of space that we want to capture for the urban air mobility corridor with eVTOLs, where we want to essentially talk about a space that's somewhere between about 300 meters to about, let's say, about 1,500 meters. Like, let's say about a 1 kilometer worth of corridor or thereabouts. And the people world over are talking about this kind of a corridor to be reserved for this new breed of aircraft that will fly by the respective regulatory agencies. So I think there is a video that could probably play out here. So we just have an animation of how we also actually should be working on air traffic control, which avoids collisions in the first place. And that could be based on developing trajectories on the go that do not intersect with other trajectories that are in flight, where you give a vertical separation across different aircraft when they have to crisscross the paths, but could probably assign the same altitudes for aircraft paths that do not crisscross. So these are algorithms that we could actually develop and get a automated air traffic control to be done, but with manual supervision, where you have the air traffic controller of the particular geography having a full view of all the aircraft that are flying, and with like a 3D rendering in front, where each air traffic flight path that is authorized automatically with the algorithm allows for this non-colliding paths, and the air traffic controller can continue to watch all of these things happening and intervene only when there is a violation of this algorithm that's happening, and then take corresponding corrective actions as soon as possible. So that's the approach that we are actually taking to air traffic control. And then another thing that we have to actually worry about is pilot training, where the crux of this entire problem is actually going to be in terms of high fidelity simulators. And we also actually have to look at scenario-based training, and then a hands-on training, integration with air traffic control, and then finally emergency response and recovery response training. The first step that we will want to do, or a 0th step ahead of all of this thing, is to build an aircraft that doesn't require too much of a pilot training in the first place. As in to say it could actually be fully autonomous, but for the purpose of regulatory compliance as well as public acceptance, we will actually put a human pilot who has the ability to do a manual override. But in reality, the aircraft could actually fly by itself from the point of origin to the point of destination with complete stack of obstacle detection and avoidance on the go, with different kinds of models that are in play when you're taking off and landing, where you have a clutter of obstacles that could actually be there, maybe static obstacles, but maybe mildly moving obstacles, could be tree branches and so on, but not exactly where you land and take off, where you will have a clear airspace vertically all the way to your flight altitude. But you need to be cognizant of all these obstacles that are around, and that's done with typical segmentation and feature recognition and all of that stuff. But while you're actually flying forward and at your flight altitude, you hardly get any obstacles to come by. So you need to actually use things like event cameras and have a attention model, which is kind of looking out for anything that moves rather than anything that is static, so that you can look at dynamic obstacles and avoid them as we go along, and develop protocols for how to actually avoid those obstacles on the go, so that, let's say, two aircraft are actually coming at each other. Both of them should not try to avoid each other in the same direction and again go collide with each other. So you need to have a protocol by which each of them will actually go away from each other while they're trying to avoid each other, and so on. So these are things that we are actually developing algorithms on. So I think this is probably like the last slide where we want to conclude with where we are today in our journey in doing all of this together, and not just the aircraft alone. What started as about myself as the one professor and about 4 students in 2017 is now actually, the slide is a little outdated. It's about 100 plus professionals that are actually working in making flying ubiquitous, is actually the way we want to look at it. Not only are we working on the aircraft, but also the air traffic control, the vertiports, and the pilot training aspects, the simulators, and the autonomy piece, all of that stuff put together. So the current roadmap is we started out incubating at IIT Madras, and then we actually showed our first eVTOL flights on a drone basis, which is like about a 1.7 meter wingspan, 2 kg payload kind of a thing. Soon thereafter, in September of that year, and went on to actually go do a eVTOL drone, which is a much larger, about a 3 meter wingspan cargo drone. And we've actually been going through like a drone certification, as well as now we are on the certification pathway for our aircraft itself, looking at doing about 2 to 3 prototypes in 2025 and getting the flights tested for these prototypes right as they are made, so that we will actually clock enough number of flights with cumulative flights from all these different prototypes through a good part of 2026, so that the later part of 2026 is when we can actually launch ourselves into an air ambulance and as well as a flying taxi, as we look at more variants of those to be certified. And of course, go back to the drones that we have made to be also commercialized for cargo and other camera-based applications like surveillance and all of that stuff. I'll thank you here, and I think we've probably taken about 40 minutes of time, right? And then I'm leaving time for the Q&A. Yeah.
Wonderful presentation, Satya. Thank you for sharing from the start to from the beginning of your adventure endeavor, and then telling us how things moved and where you are today on the activities of ePlane. Thank you so much. In fact, yeah, we have for all the participants, here is what you can do. You could type your question on the chat, or you feel free to unmute and ask a question. Okay, and I have several questions, but I will wait for, I'll give priority to the participants. Yeah, please feel free to ask the question. I see one question from Mark. Please go ahead. Please go ahead and unmute if you can, and then bring up the question.
Hello, good morning or good afternoon. You mentioned a high percentage of maintenance.
The volume is pretty low, right?
Yeah. Yeah. Can you increase the thing? Or
Sure. The high percentage of maintenance.
good.
Why does electric power system need a lot of maintenance? Is this high percentage of a smaller amount, or what is it that needs maintenance? I've heard this mentioned before.
Oh, the electric. So I think what I was saying is when compared to engine-powered aircraft, the maintenance is pretty low. If you look at the current engine-powered aircraft-based aviation, 30% of the cost is actually maintenance, whereas we feel that could actually come down to about 10% of current costs, and therefore we think about a 30% maintenance, 30% operations, and 30% fuel. The operations could actually include pilot costs plus lots of other ground support costs and so on. We can actually eliminate about 1/3 of the maintenance of what we have today. About 20% will be gone, and another 20% could actually be shaved off on the operating cost. Plus, I also mentioned the asset costs that can actually be brought down so that the lease repayments and all of that stuff can actually come down. So that's where we are able to look for about a 50% reduction in cost for electric aviation and current aviation.
Okay, thank you. My second question was about hardware. Do you have hardware demonstrators? Do you have vehicles? Are they flying? Are they being tested?
Yes, as we speak, we had actually successfully demonstrated flight of a 3 meter wingspan, 3 meter nose to tail eVTOL that can carry 50 kgs of payload. And we are on our way to now building the first prototype of the 3-seater eVTOL, the passenger eVTOL, or the air ambulance eVTOL, which we expect to complete by April. And correspondingly, we have actually been doing lots of ground testing of lots of the subsystems and components as we speak, like the motors and the battery packs and all of that stuff. Yes. all of that work is ongoing.
Yeah, thank you.
Yeah, so there is a question from a student, I believe, Grishma. She's asking if.
I think if you connect with me on LinkedIn and send me a
Thank you.
message.
Yeah, please. Yeah. Okay, so Satya, but in the meantime, while other people might be asking other questions, how are you working with the government, like DGCA, for example?
Correct. So I think the DGCA was clued in on this a bit early on, about 2022. We actually went and met them and sensitized them to the whole thing, and then they brought themselves up to speed. In early 2023, we applied for the design organization approval, and I think I shouldn't say early, maybe late December of 2022. And we actually got the design organization approval pretty fast. I think they fast-tracked the whole process with all the audits and stuff that they needed to do month on month. And we got the design organization approval in May of 2023. And that was pretty important because we are actually the first private aircraft company in India to get a design organization approval to build a full aircraft, that too an eVTOL. Subsequently, they have had a letter of intent and followed by an MOU signed with EASA for exchange of best practices. They are doing something similar with FAA. This last year, they set up two subcommittees, one for vertiport standards, another one for aircraft certification standards. Those committees submitted the report and it went through public consultation. Feedback from people like us as stakeholders, and they have now released the advisory circular on both vertiport standards for India as well as the aircraft certification standards. So, which is taking into account features of EASA's standards as well as FAA and ENAC of Brazil. So we are now following that as a certification basis for our certification process. We have initiated that. We are going through our propeller certification with them based on European standards. And apparently we are the first ones to actually go through a propeller certification at all, and so on. So, so there's been like a lot of work that we are doing with them together. The next thing that they're actually working on is pilot training standards, and the last part that they will, there are two more. I think they also are actually looking at a MRO subcommittee. Of course, they will have to give us a production organization approval as we go along when we do the prototyping and start flight testing. And they also actually will look at air traffic control towards the later part of this entire period by the time we get to service.
Wonderful. That's quite a lot of work. I'll again open for the participants. Anytime you have a question, I will stop. So please feel free to unmute and ask the question. So
I do have a question.
Please go ahead.
Yes, so in all these high power electric propulsion for eVTOLs, what is the most promising battery architecture or battery chemistry, like solid state or silicon anode technologies would be most promising for this kind of
right. Yeah.
technology?
So the jargon that we use in aviation is what's called as LRUs, which is line replaceable units. So the way our design architecture is to actually be chemistry agnostic. Chemistry means not just saying lithium ion, but what is anode, what's a cathode, any of those kinds of things. But we could actually then transition to a lithium sulfur or any other chemistry and so on. The challenge here is actually getting good power densities as well as energy densities. So if you're actually looking at the Regoni plot, you need to be somewhere up there on the right-hand side as well as a little bit to the top. So energy densities as well as power densities is actually the biggest challenge that we look at. But going forward, there is an outlook that we could actually model battery management systems and battery thermal management systems to be actually chemistry agnostic by looking at these batteries and cells, each and every cell as an electrical unit with its internal resistance, inductance, capacitance. So it's essentially bring them into an LCR circuit, characterize their resistance, capacitance, and inductance, and so on. And once you actually have that kind of a circuit-based model, we should actually have a overall energy management system that could even include a multi-chemistry architecture, where you could say, I'm going to count on one particular chemistry worth of battery packs for getting the power, but I want to actually have another battery pack for the energy, and so on. So there are these multiple options that are available on the table for designing an eVTOL such that I have my electric powertrain coming back from my propeller to maybe if I have to have a gearbox, and then the motor, and then the motor controller, all the way back to the battery, and where the battery has to actually supply the required C rates, I can actually have a combination working there with a power converter and an energy management system that actually delivers the required C rates to the powertrain. So we can actually look at these two independently as subsystems, but we need to actually integrate them to work together. So this is the way we are modularizing our design concept, so that we are not dependent or beholden to any one particular chemistry throughout what we do.
Right. So would it also help with rapid charge cycles and all of that, so we can charge the battery really quickly
Yeah,
and discharge it
that's
relatively.
that's a very good question there. There are a few things that we have to worry about. One is, for example, what's the kind of voltage stability that we get through the discharge process? Second, how the voltage actually holds up across different parts of the life cycle of the battery. Where will I actually have like high voltage at start of use of the battery versus end of use of the battery, and so on. So we have to always look at what's the kind of the life cycle that we will get from this battery, and what will actually be the voltage stability of the battery pack through this entire life cycle. Because ultimately we have to design our powertrain for the lowest voltage that I can get through the cycle of the battery. But larger the number of cycles, larger the number and less impact on the battery life due to fast charging or desirable properties. But that's actually kind of like a no-brainer, even from the road vehicles standpoint. But the numbers will actually be slightly different. We are talking about number of cycles could be in the 1400s, 1500s kind of thing, minimum. Plus, we want to actually make sure that the life does not degrade just because you're doing a fast charging significantly by more than about 100 cycles or so, and so on. So these are characteristics that we look for to make the aircraft economically viable.
Right. Thank you, sir. Thank you very much.
While again waiting for other people to ask questions, one question I have is, can you share some information on the details about autonomy? For example, autonomy of aircraft is one aspect,
Yeah.
with all the sensors and all that. On the other hand, how do you make sure that all the software, any associated software things, for example, in the US, we have NASA is leading this program, Advanced Air Mobility National Campaign, and in that process, we built an ecosystem with a platform as well as community, and then all the many services. For example, a simple thing is like traffic management. Then there are specific software services like weather service and something like a data exchange hub and all that. So can you share how are we handling the autonomy aspects?
Right. So our approach to actually developing autonomy is through drones. So a lot of applications that you mentioned can actually be done with autonomous vehicles, which are essentially drones. And drones can come in different sizes and shapes for different purposes. At ePlane, we actually have drones that start from of course, the multicopters, which are standard short distance variety, to a short wingspan, a 2 kg payload capacity kind of eVTOL. And then we actually go to this 50 kg payload capacity eVTOL that's about a 3-meter wingspan. And we have the ability to also go to a 4.5-meter wingspan, 100 kg payload capacity. We have internal designs on that. Not really decided on whether we want to actually implement it. But the reason why I'm actually talking about larger and larger aircraft is from an autonomy perspective is it allows for the available real estate to mount more and more sensor stacks, and secondly, the weight budget that it can take. And the third one is a cost budget, because many of these sensors are expensive. If the overall aircraft is larger and it has actually a better utilization capacity, then there are people who will actually be willing to pay for all of the autonomy. And the larger aircraft actually, for the larger and larger aircraft, the autonomy becomes more and more important, particularly if you're looking at unmanned aerial systems. So we have this large space like wings and the nose and the top of the aircraft and the bottom, all of these locations where we actually get like a 360 steradian worth of mapping of the the situation around it for a situational awareness. And we do this with a combination of cameras, lidars, and radars. So radars actually give you the longer range, but lidars can actually be much more have higher resolution over a shorter range, and cameras will have much lesser range but much better resolution. And here again, we have to actually look at a few different kinds of cameras. One of them is let's say the normal cameras that are mounted in different parts looking at different directions. The second one is stereoscopic cameras for actually getting a depth perception. We also actually develop algorithms for what's called as monocular depth perception, where we can use existing normal cameras, but just by virtue of the motion, we can actually evaluate the depth of the images that we are looking at in these cameras. The fourth one is what's called as event cameras, where we will want to actually look at any obstacle that is moving that gets captured by the camera better than a stationary obstacle. So there are a bunch of these different cameras that we would actually try and do a sensor fusion along with a lidar or a radar, so that we will actually be able to get the two-dimensional image as well as a depth associated with it. And with this coupled with the corresponding software in terms of segmentation and feature detection around a vertiport for takeoff and landing, plus a computer vision algorithm for doing a precision landing right on top of exactly where we want to land within a few centimeters of error. These are things that we actually pack into our aircraft, and we have demonstrated these starting from the drones. And lastly, also actually switch from segmentation models to attention models while you're in flight, so that you can actually detect dynamic obstacles without having to search for obstacles that guzzles processor power. So the processor basically wakes up only when there is an obstacle instead of actually searching for obstacles when there are none. So there is like a whole set of architecture that we have to think about on putting all of them together. And that's possible for us to do at the level of about a 50 kg payload drone or a 100 kg payload drone before we get into the manned aircraft. And when we get to the manned aircraft, regulations are, do not allow us to do a full autonomy. We need to actually convert all these things into pilot assist features that will actually display on the pilot screen with alerts to the pilot for obstacles, and also get the pilot's permission for a manual override, so that you can actually autonomously try to avoid obstacles when you have these quick obstacles that are coming ahead of you. So that's again the next implementation that we have to do while interfacing with the pilot.
Thank you, Satya. I think that's pretty for explaining all the details. And I have more questions, but I will ask one last question from the audience, from the participants. Luzan is asking, for the large drones, is there any standard way to test the eVTOL battery characteristics?
Yeah, so the reason why we are actually doing the large drones is because the large drones are just about an eVTOL minus, the passenger eVTOL minus. The standard way for us is actually to have a battery tester of that particular capacity, so that we will be able to apply the not just the load, but also the duty cycle that corresponds to an eVTOL, because the kind of the power surge that we will have during takeoff, and then it actually comes down during forward flight, and again there is a mild surge when you're actually trying to land, is kind of unique for eVTOLs when compared to conventional planes or even cars to a large extent. And what we have to worry about is when the power really surges, will actually the voltage come down, and will the voltage be sufficiently high enough for the motors to work at that time. So the load and the ability to mimic the load in this duty cycle is actually very important for our the battery testing. So we actually have battery testers that mimic this particular load and the duty cycle with the voltage fluctuations that we anticipate from the cells, so that we can do a proper testing of the battery on what C rates it can deliver at what points of time.
Yeah, so I see a couple of comments from participants. They're appreciating it's a great presentation. And on
Thank you.
that note, we will end the webinar. And thanks for everyone for joining. And if you are not a member of IEEE VTS Vehicular Technology Society, please join. And this video and the presentation will be made available on a portal called IEEE Knowledge Portal that is hosted by the Vehicular Technology Society. Once again, thank you, Satya, for giving a wonderful seminar. And thank you again. We'll have a wonderful rest of the day. Thank you. Thank you. Bye.
Thank you, Kamesh.
Bye. Thank you. Thank you, Mark.